Observe the illusion of a spoon bent in water. This is refraction, the bending of light as it moves from one transparent medium to another. It happens because light changes speed. Light travels fastest in a vacuum. When it enters water or glass, it slows down. If the light hits the new material at an angle, this slowdown forces the path to bend, a fundamental principle that governs all optics. We quantify this change using the refractive index, or N. It is the ratio of light speed in a vacuum C to its speed in the medium V, equals N equals CV. For any material, N is always greater than 1. A higher N means the material slows light down more. This constant index allows engineers to precisely predict and control light behavior in any optical system. The exact calculation of light bending is defined by Snell's law. 1 sin equals 2 sin 1 cd equals n to sinner. The angles are always measured from the normal line. When light goes from a faster medium low 1 n1 to a slower one high 2 n2, it bends towards the normal. Snell's law is the mathematical bedrock for designing lenses and ensuring the correct path for every ray of light. The most critical optical effect is total internal reflection. It happens when light tries to move from a higher index material to a lower index one. If the angle of incidence exceeds the critical angle, the light cannot escape. Instead, it is perfectly reflected back into the original material. This 100% efficient reflection is the engine behind all high-speed fiber optic data transmission. An optical fiber is built to leverage TER. It has an inner core and an outer cladding. Crucially, the core's refractive index is slightly higher than the cladding's. This index difference creates the necessary boundary for TER. Once light is launched into the core, it is trapped, bouncing perfectly off the lower index cladding walls, ensuring the signal travels over great distances. The data travels by light pulses bouncing continuously in a zigzag pattern down the core. Because this reflection is total internal reflection, the signal maintains its strength with minimal loss, even over thousands of kilometers. This resistance to loss and immunity to electromagnetic interference makes fiber optics superior to traditional copper for massive bandwidth and long-haul communications. To transmit data, we use modulation. Digital data zeros and ones is converted into light pulses using a high-speed laser. A binary 1 is a pulse of light. A binary 0 is the absence of light. At the receiver, a photodetector converts the incoming light pulses instantly back into electrical signals 1s and 0s, completing the digital communication loop with incredible speed and accuracy. Fiber optics is the essential infrastructure of the modern world. It powers submarine cables that connect continents and brings high-speed internet directly to homes. FTX. Beyond the internet, it's used in sensitive sensors and medical endoscopes. By harnessing the simple principles of refraction and TER, we have built the global, high-speed nervous system of the 21st century.